This is Anita Wood, and welcome to this topic snippet video that introduces one of the programming paradigms used in software development today, Object-Oriented Programming, or OOP. There are two primary methods of programming in use today, procedural and object-oriented. Procedural programming is centered on creating procedures, and object-oriented programming is centered on creating objects. We're going to start with a brief discussion of the procedural programming paradigm. This will help you have a better understanding of the benefits of object-oriented programming. Also, many times it'll be up to you to decide which programming paradigm you should use to solve a particular problem, procedure, or object-oriented. Knowing about both paradigms will prepare you to make that decision. The concept object-oriented programming is important to learn when you're learning programming because you'll be interacting with object-oriented languages during your programming career. That's because industry standard languages like Java and C# are object-oriented programming languages. The earliest programming languages were procedural, meaning a program was made up of one or more procedures. A procedure is a set of programming statements that, together, perform a specific task. The statements might gather input from the user, manipulate data stored in the computer's memory, perform calculations, or any other operation necessary to complete a task. Procedures typically operate on data items that are separate from the procedures. So in a procedural program, the data items are commonly passed from one procedure to another, as we see here. As you might imagine, the focus of procedure programming is on the creation of procedures that operate on the program's data. However, over time, and with the need to solve more complex problems, programmers found the separation of data and the code that operates on the data often led to problems. This led to long and complex code that was difficult to test and maintain. Another issue involved making changes to data. Data stored in a variable, which is defined to have a particular format, say integer or number. The procedures that operate on the data must be designed with that format in mind. But what happens if the format of the data needs to be altered? This can happen when a program's specification changes. For instance, a specification change could result in the variable that holds a date to be changed from a number to a string. This change would result in not only a redesign of what the variable's data format is, but also the code that operates on the date must be changed to accept the new string format. So, changing any code that manipulates the format of the date variable is needed, as well as changing any method calls or method definitions. If the programmers aren't careful in implementing these changes, you can see that it could lead to the introduction of software bugs. Here's an example code using the procedural programming paradigm. The program will input, store, and print your age and your friend's age. The bottom portion of the code is the main procedure, which defines the variables and calls the two procedures that are responsible for the tasks of getting the age and printing the age. Procedure A gets the age, and procedure B prints the age. Because the data is declared in the main procedure, the getAge and printAge procedures must have the age variables passed to it as arguments. Also, the getAge procedure must return to the main procedure the age that was typed in so it can be appropriately stored in the associated variable in main. Whereas procedural programming is centered on creating procedures, object-oriented programming, or OOP, is, as we said, centered on creating objects. Now, there are many terms used in OOP we need to discuss so we can understand the underlying concepts of OOP. The first term is an object. An object is an abstract entity that contains both the data and the procedures. Here we go, more terms. The data contained in an object is known as the object's attributes, or data, or characteristics, fields, or properties. And the object's methods are also called actions, procedures, behaviors, or functions. These methods work on the object's attributes. Because objects consist of both the data and methods, they are called a self-contained unit. Think of your alarm clock as an object. It has the following attributes: current second, current minute and hour, the time the alarm is set for, and whether the alarm is on or off. As you can see, the attributes are merely data values that define the alarm clock's state. You, the user of the alarm clock object, cannot directly manipulate these attributes because they're private. To change the attribute's value, you must use one of the object's methods. So here are some of the alarm clock object's methods. Set the time, set the alarm time, turn the alarm on or off. Each method manipulates one or more of the attributes. For example, set time method allows you to set the alarm clock's time. You activate the method by pressing a set of buttons on the top of the clock. By using another set of buttons, you can activate the set alarm time. In addition, another button allows you to execute turn alarm on or turn alarm off methods. Notice that all of these methods can be activated by you, who is outside the alarm clock. Methods that can be accessed by entities outside the object are known as public methods. Now, the alarm clock also has private methods, which are part of the object's private internal workings. External entities such as you, the user of the alarm clock, do not have direct access to the alarm clock's private methods. The object is designed to execute these methods automatically and hide the details from you. So here's some of the alarm clock's object private methods. Increment the current second, minute, and hour, and sound the alarm. Every second, the increment the current second method executes. We don't need to interact with this method, nor should we be allowed to. Only the alarm clock itself is concerned about incrementing the seconds. Now, you probably never give this much attention to an alarm clock before, but it's a good representation of an object that you can emulate using software. So, an alarm clock is just one example of an object that can be emulated by software. Here's a few more. A car, with its attributes of model, number doors, or engine type. It has methods for move forward and shift gears. How about a phone with attributes model, phone number, and type? You have methods to make a call or receive a call. And a person with attributes of color of the eyes, color of the hair, and the height. And the methods are sit down or run. So how is an object like an alarm clock created in OOP? Now notice in the previous slides, I placed quotes around the term object. That is because the term object is used to define the concept of object-oriented languages and also used in the implementation of an object-oriented language like Java. So I'll rephrase the question. How do we take the alarm clock object, in quotes, and emulate it in OOP? Well, first we need to define the term class. A class is a blueprint for creating objects in OOP. Notice this time, objects is not in quotes. Just hang on to that thought while I finish up defining classes. We're all familiar with a blueprint. At the left is a blueprint of a house, And at the right are the houses that were created from that blueprint. The blueprint provides the builder with the house with the details, the attributes, and the methods that they will use to build the house. The attributes include number of windows, number of bedrooms, the street address. Some of the attributes are the same for all the houses, but there are some that are unique to the house that is being built. For example, all houses might have one front door, but each has a unique street address. Methods can be turn on lights or open windows. All the houses share the same methods. So back to our alarm clock discussion. To be able to create an object, unquoted, from an alarm clock, for the alarm clock, we now know we have to create a blueprint for alarm clocks called a class. So here are the attributes and methods that we discussed earlier as they might be defined in an alarm clock class. A best practice for creating classes is only the class methods may directly access and make changes to the class's attributes. The attributes then are made private. The methods used to change the attributes are public so they can be accessed from outside the class. On the other hand, private methods cannot be accessed from outside the class. We talked about which methods should be private and which ones should be public for our alarm clock, and we set them here. Now we'll talk about the public and private modifiers, as they are called, later in the module. Here's the sample Java code for our alarm clock class. Notice not all of the details are here, but you should be able to see the process. You're going to have an opportunity to practice creating a class, but right now, this code is just to show you what to expect later in the modules. We have the class blueprint. Now we're ready to create objects from that blueprint. Like the house blueprint gives the builder all the information they need to build the house, a class provides all the information the software developer needs to create objects. What the software developer does not need to know or want to know is the specifics about how the attributes are declared or how the various methods are coded to implement the behaviors needed for the object. Before an object can be used in code, it must be instantiated. We create an object from a predefined class through the process called instantiation. Instantiation is a complex process where much of it is done by the programming language, but there are some things the developers must also do, and we'll look at what the developer does later. For now, here is the example of the Java code for instantiating an object called AnnaAC from the alarm clock class. The object that is created through instantiation is called an instance of the class. So AnnaAC is an instance of the alarm clock class. Now, the developer can use AnnaAC to represent a specific alarm clock, perhaps the alarm clock they purchased for Anna. The AnnaAC is a specific example of the alarm clock class. So the developer will set the unique values to the attributes for AnnaAC. Here, current second is set to 34, current minute is set to 35. The alarm clock class can be instantiated again, and this time the object reflects Jim's alarm clock. Again, the developer defines Jim's attributes to those unique from Anna. At no point will references to Jim's object interfere with Anna's object. So Jim's current second is set to 53, current minute to 56. Anna's attributes remain the same. We talked about how the object defines the attributes. How does the object use the class methods? The methods are just called as normal, but the call includes the name of the object. Notice here is a method call to set time. The object and instant name, AC, prefixes the method named setTime. This syntax is called a dot notation because it uses the dot operator. More importantly, the variables the method uses are the ones specific to the object. The developer will call setTime that modifies the hour, minutes, and seconds for Anna's alarm clock by using the method call shown here. In the setTime method, the variables that are modified are the ones associated with Anna's alarm clock, the current second and the current minute. Here is a more complete example with Java code using the same application we wrote earlier, getting and printing your age and your friend's age. This time, the code uses object-oriented programming paradigm. Now, there's a file which defines the class age and another which defines the main method which uses the age class. The box in the code to the right shows the instantiation of the objects your age and friend age in the main method. The rest of the code in the main method shows how the instances or objects will be used. A few things I do want to point out is first, the same age class is used to define both your age and your friend's age. When the method getAge and printAge are called, there are no arguments. Thus, the data is encapsulated or contained in the object age, so we don't have to pass them back and forth. Also, these methods do not return values because, again, the data is encapsulated in the object. The call to the getAge method associated with the yourAge object will only have access to the attributes associated with the yourAge. Same with the printAge method. Following the green line above, you see how the getAge for yourAge object has the number 27 inputted, and the printAge for the same object prints the correct age, 27. The red line shows the same method calls, but for your friend's age, input is 54 and output is 54. This shows the attributes for the two objects are separate from each other, and the methods will only modify the attributes associated with its objects. Though there's more code represented here, the code, particularly class age, is reusable. We can easily add other objects called mom's age, which would be used to get and print your mother's age. This would only require 3 more lines in the main method, and no changes needed to the age class. Again, we're going to be discussing the concept of class, objects, and the required Java code later in the module. But for now, this concludes the introduction to object-oriented programming.